There you go. All right, what's up, guys? My name's Curtis. This is Cody, and this is going to be a convolutional network workshop. So it's kind of broken into like 3 parts, more or less. We're going to just have a really fast recap of neural networks. So we had covered that in the previous workshop, but we'll just try and answer the questions and really breeze through that real fast. Second part, we're going to go into practical training. So we're just going to explain different optimization methods aside from gradient descent, such as atoms, using momentum, L2, etc., etc. So these things are foreign. Hopefully you'll at least get exposed to it by the end of this workshop. And the third part, which is the non-dry part, is going to be the actual convolutional networks content. So we're going to show you guys how these work in code, how you can build image classifiers with these, and we're going to have like a actual comp sci demo with that. So, so this is just the outline. Neural networks. So just show of hands. I don't know if there might be a few new faces in the room. So who here was here for the first workshop? If I could see. All right. So out of those people, who here remembers what gradient descent is, or just like could explain deep neural networks? All right. So I'm gonna recap this a little bit. It's all right. So a neural network is basically just some function that we're trying to magically map some inputs to some labels. So we just want to give it some inputs. Let's say we're trying to estimate how much a house costs. You'll just give it some features such as how many windows are in the house, where is the house, how much does it cost. It's going to do some fancy math, and it's going to output some value, the value being, like in this case, an actual price. So we can also use neural networks to, let's say, do image recognition. So let's say you want to make a network that can tell the difference between like cats and dogs, or tell the difference between like me versus my grandma. You can feed it pixel images, being a pixel is just a 3-dimensional vector, so that stands for RGB, red, green, blue. So you can just feed in like an array of pixels flattened into like some input layer. It's going to do some computation on that, and it will output, let's say, value 0 being like I am my grandmother, 1 being I am myself. So how deep neural networks tend to be structured is in the first few layers, they tend to recognize smaller or simpler features, such as edges, maybe just some colors, some lines. And then the more layers you add later in the layers, you get more abstract stuff, such as, is this an ear? Is this a face? Can you analyze the entire stock market in like a later layer, et cetera, et cetera. So adding more layers to a network allows you to increase complexity. And yeah, how it updates the weights, it uses the process called gradient descent, so we're going to cover that in a bit. But yeah, that's just a very brief recap on neural network structures themselves, or just simple neural networks. So now into the practical training. So gradient descent. Can everyone just put up fingers between 1 to 5 of how comfortable are you with this topic? 1 being I've never heard of this before, 5 being if I asked you to do this by hand, you're like good to go. So I'm just looking around because I want to know how much I should go into. All right, cool. So gradient descent, if you guys recall, is simply the process of finding some loss function and traversing down this loss function. So what is a loss function? A loss function is when we want to train our network, first we want to know how bad is it doing. So let's say the case of we're trying to estimate the cost of houses. First we want to have our training set, which is, let's say, all the houses in Boston, and we then want to predict a price for each house. After we predict, we're just going to see how off our prices were from the original house. So let's say you thought the house would cost like $5, it cost $16,000. Difference between that is going to be a pretty large number. That's going to be a large loss. You're going to add whatever that loss is to like other losses throughout the network. So we kind of think of a loss function as this graph. So you'll see at the bottom of the graph is going to be like an optimal point, because that means your loss is low, your error is very low, and you're doing very well. If you're high up on the graph, you're doing pretty bad, because there's like a 15,000 difference maybe in the house prices that you're estimating. So gradient descent is a technique that allows us to use calculus to traverse down this graph. We're trying to find some local minimum that would essentially give us some local optimum values for weights within our network. So remember this graph from this image. If you guys were at the first workshop, these lines represent various weights and biases. So we're simply trying to fine tune these weights and biases such that our output is quite optimal. So just to recap, we're trying to traverse down this graph to some local minimum. That way we have some low costs and we're doing pretty optimal across our data. So how do we do that? gradient descent update rule. So gradient descent, the update rule, after we calculate some loss, we're going to calculate a derivative. So let's say this simple case. We just have some loss function, j of w, and let's say this is what our loss is with respect to some weight w. You'll notice that like right here we have some gradient. This gradient is going downward, so it's negative or less than 0. Here it's going to be positive, so it's going to be greater than 0. If we subtract a negative number, it becomes positive, hence why we're subtracting here. So by subtracting a negative number, it would cause our weight to move to the right, which will then push us down this curve until we eventually reach here. If it is positive, however, then we simply want to subtract it. By subtracting, it moves it to the left. So by finding the derivative of our loss function with respect to our weights, we're able to update our weights in the direction that gives us a slightly lower loss. So we're simply going to repeat these steps. It's an iterative approach until it converges. Once again, we have an alpha term, so that stands for our learning rate. The learning rate is just some value between 0 and 1 that represents how big of a step you want to take. For example, if the step was like 10,000, the reason why it's between 0 and 1 is if it was like 10,000, you might just overshoot and move like all the way up here. That doesn't help. So try to keep it relatively small. And this term right here, the dj d theta, once again, is just this gradient of whether it's going down or up. And then we're just moving that direction. So that's all we're doing. We're just traversing down and updating all of our weights accordingly. If you guys start using machine learning frameworks such as PyTorch, TensorFlow, and Keras, it'll be calculating these weights automatically, so you don't have to do this part. All you gotta do is specify what is your loss function, and then it will automatically calculate the gradients, and then you can just subtract them as is and set your learning rates. So as you saw on this slide, there are 3 different ways of doing gradient descent that we'll discuss. So batch gradient descent is kind of just a general term. So for this, every time we update our weights, first we're going to sum up across our entire training set. So if you have a training set, let's say 1 million samples, you have to do go through our loss function 1 million times before we update anything. And we're going to do that constantly. So instead, we can use something called stochastic gradient descent. Stochastic gradient descent, we're going to basically update our weights for each individual input. So what that means is it will be really noisy. For example, let's say you're trying to train a network to tell the difference between cats and, just to tell if something is a cat. If the first thing it sees is a tree, it's not going to know, what the rest of the data is. So it has to see more stuff, actually see what a cat is, be told this is a cat before it trains. So on the first iteration, it's going to be really noisy across each individual update step, but eventually it will slowly converge once it sees enough objects in its lifetime. So stochastic gradient descent, just to reiterate, we're simply updating our weights across every single input that we receive. Whereas batch gradient descent, we do it after we calculate the loss across the entirety of our training set. So mini batch gradient descent is going to be some middle ground between stochastic gradient descent and just batch. So mini batch allows you to set some size. Let's say I want to see 64 images, and then we're going to calculate our gradients then. So it's kind of just like middle ground between the two. So here we just, and you'll notice it's still going to be noisier than gradient descent, but it's not going to be as noisy as stochastic. So this is just some graph, just to recap everything. Batch gradient descent is very slow because we have to go through our entire training set before we update anything. Mini batch, we can set the size, so it's like a medium speed, and there's a bit of noise, but not too much. Stochastic has a lot of noise, but it trains really fast because we're updating after every individual sample set. All right, now we're going to talk about some optimization techniques. Just out of curiosity, who here has heard of atom optimization? Raise of hands. Okay, so out of you two, who here actually could think they can implement this, or actually knows what's happening under the curtain? Yeah, so atom is a very magical thing until you actually play around with it. So for those of you who might not know or haven't worked with machine learning frameworks, gradient descent tends to be really slow. So for gradient descent to work, you might have to set a learning rate of 10 to the negative 8, or that's just a really, really microscopic number. So it causes it to have to train a lot of times as it's taking really small steps. So instead, atom allows you to basically increase your learning rate, and it'll learn just faster, and it works way better. in comparison to gradient descent for like majority of problems. So before we go into Atom, we're going to cover momentum and RMS prop, because Atom is basically just combining these two concepts. I'm kind of just getting exposure. I'm not expecting you guys to understand what this is like off one workshop, but like at least you'll get some high level insight into how this works. So momentum, if you guys recall in this image, you'll notice these training steps aren't going in a straight line towards some local minimum. They're kind of noisy in various directions. So if it's moving upwards or downwards, let's say this was just a 2D graph, for example, then that's just like, we'd rather not have that noise, because we would like, the fastest training method would be if we can draw a straight line straight towards this centroid.
Is it actually going to be a straight line?
Yeah, it's curved, but like straight line relatively, like through the curve. I don't know how to conceptualize that.
I don't know what this graph is.
Yeah. All right. Well, more of the story is we want to find the shortest path to the centroid without doing all this randomness. So, as drawn here, let's say this is some graph. So this is topology graph. I think you guys might know what like x squared is. It's a parabola. So imagine this is just x squared in like 3 dimensions. So here I'm just going to define some axes. So there's B and W. These are very magical axes. I'm just trying to make a simple pictorial for you guys. But what B and W would really represent, if this was a real world thing, is like, let's say 5,000 different hyperparameters. So basically this is your loss function with respect to your weights. And I'm just trying to make it in 2D so it's like a little easier to conceptualize. But like in all reality, these are going to represent like an unimaginable like vector space. So it might be like, W might be like 8,000 thetas or whatever your actual network is. So our goal with momentum is we want to shrink how much our loss oscillates in between training steps. So you'll notice that when we're training, this blue line, it goes really far upwards, it oversteps again. It keeps overstepping until it eventually converges to some local minimum. So if we took the average of how much it's vertically going, the average is going to be about 0 because it goes up, goes down. So that's relatively just like going to cancel out. Whereas if we take the average of it going to the right or just towards the centroid, it's going to be like some vector actually pointing this direction. So the goal of momentum is to shrink how much it oscillates up and down, but maximize how much it goes horizontally, such that we reach the centroid as fast as possible. Because the fastest way to get to some point is to go straight there, more or less. So momentum does this by using exponential weighted averages. So if you guys have done anything with stocks, you might know what like a MACD line is, or you might have just heard of this term, exponential weighted averages in general. It's basically just a mathematical way of smoothing over a graph. So it uses a sliding window, which just takes the average of, let's say, all numbers within some time frame, and then moves it across. So like this point is going to be the average of every, let's say, day for the last 30 days. So by averaging, we use a very similar, well, pretty much identical function when using momentum. So we're going to take the average of the loss for each point. So like you'll see the average is just going to become 0 when it comes here, and then it just smooths down. It goes in this general direction down the slope. By doing that, it requires us to take way less training steps, as it will just converge faster. So just get that concept in your head. We're simply smoothing down the loss function such that we converge faster to the centroid. So the actual math for this, it looks like this. So this is just like the formula for an exponentially weighted average. So the difference between using momentum and just plain gradient descent is in your update rule. For just gradient descent, it's going to be theta minus alpha times like dj d theta, whereas here it's going to be theta minus alpha times this velocity term, using velocity in air quotes. So this term is simply going to be the average of your thetas across some time frame. And this beta thing you see here is simply going to be some hyperparameter, usually specified, so I think like 0.9, and use that to cancel out to make more plots closer to where you currently are more relevant. So yeah. Just to step on, so RMS prop kind of develops this idea even further. So RMS prop is going to take the squared gradient in this average, exponential moving average, and we're going to divide the dj d theta term by this term right here, which is kind of like an acceleration thing. The reason why we're doing this is, if you recall, we want to maximize our speed going this direction, but minimize how much it oscillates up and downwards. So if we'll also notice this gradient of it oscillating up and downwards tends to be really large. So if you're dividing by a very large number, it basically decreases it, which causes this to change little, whereas we'll be increasing how much it changes here, because we'll be dividing by a smaller number. Divide by a small number just increases. So that's just kind of a very high level intuition of like how this works. And by combining momentum of the velocity term and this kind of pseudo acceleration term, we get Adams optimization. So it's simply going to be the momentum velocity term divided by that ST that you saw in RMS prop. So this is just learning rate. This value, sometimes your RMS prop value might be 0. So if you divide by 0, you're going to get an abnormally large weight. So instead, we're just adding some noise, usually like 10 to the negative 8, just so it's not, exactly 0. And that's how ADAM kind of works in a nutshell. I think ADAM stands for Adaptive Momentum Estimator. So yeah, it's just automatically scaling your momentum thing. So it's very high level. Don't expect you guys to like be convinced with the math, because I kind of just breeze through it. It's something if you look at it more and research this on your own, become more comfortable. But just know that ADAM, if you take nothing away from this, it's simply building upon momentum in RMS prop, and it's trying to reduce the oscillations of your loss function. So the second to last thing we're going to cover in the practical training section is overfitting versus underfitting. So these are terms you'll hear a lot when it comes to machine learning. An underfitting model is one that's simply, for lack of a better word, just bad. It doesn't have enough variance or complexity to learn some set of inputs. So an example for this would be, let's say you have two classes. So let's say these X's represent dogs, and circles represent cats. You want to distinguish between the two. We distinguish between them by drawing a line between them. If you can only draw like a 2D line or like this, you'll notice that these inputs are kind of bent, so it just does not separate these two classes well at all. So this would be a more appropriate boundary decision line between these two inputs. So underfitting is pretty indicative that your network is simply not intelligent enough to like figure out what the actual mapping is from your inputs to your outputs. Overfitting, on the other hand, is when it's like just too complex. It learns how to estimate your inputs exactly. So while that might seem like a good idea, maybe presumably in some of your heads, like later on we'll show why this is actually really bad. This tends to be a little trickier in how we actually achieve this. So underfitting, just to recap, is when you have a too simplistic model and it doesn't describe the data well. So we can solve this by simply slapping on more neurons to your network, which means adding more hyperparameters, slapping on more layers to your model. That will increase the variance within your model and allow it to just learn more complicated problems. You can detect underfitting if you just straight up have like a lot of loss. So if your model isn't learning anything, it's likely it's being underfit. So just try adding more features and hopefully you'll get better results. So overfitting. So imagine this is just a sine function. So sine moves kind of like this, traverse throughout the graphs. If you're overfitting and you're running your training data exactly, you might get something that tries to regress kind of like this. So you'll notice that like this doesn't generalize to other points. Let's say we want to predict a point being over here. We have no idea where this function is going to go. It might just like go straight downwards towards infinity. It's too wild. There's too much variance in between its weights. It's not good at generalizing for other things that it hasn't seen before. It simply knows what it's seen exactly. So how can we detect overfitting if our data is going to do this? Because if it's doing this, then our loss that we're calculating is going to be approximately 0. We can do that by actually looking at our train set versus our validation or test error. So show of hands, who here knows what test error means or validation error? So train error is the loss we get across our training inputs. So when we're training, we tend to divide our data into multiple sections. We'll have some train data, which the model never sees, and then we'll have some test data. So you can think of train data as like if you're studying for a test, it's the practice problems your teacher assigns, whereas the test itself is what you're handed in class, and that's going to be your test set. So if you do well in train data, but so you see it approaches 0 and it's constantly going down, so it's doing really well in the practice problems. But then it sees some test data that it's never seen before, and then it just like eventually starts getting worse and worse as validation because it just becomes like more of this kind of function instead of being able to generalize. So if you see a loss function where you're plotting your test error or how bad you do on the test versus how bad you did on the practical, on the practice problems, it'll look, and its overfitting will look similar to this. Alternatively, it might just, in general, if your test error is just increasing as your train error goes down and it's diverging, that's usually indicative that you have an overfit problem. Another way of detecting overfitting is if your weights are abnormally large. So if you have really large like parameters, then you might get this fluctuation in your function because they're very sensitive. So that leads us into L2 normalization. So L2 normalization tries to shrink really large weights. It does this by basically taking a derivative from this function. So if you guys recall, can anyone tell me just off the top of their heads, this lambda times theta squared, what is the derivative of this half of the term with respect to theta? So I'll tell you right now, lambda just equals 0.5. So if that just sounded like convoluted, if I asked you to take derivative of x squared times 5, what would that be? Yeah, so in this case with theta, if you take derivative of this with respect to theta, it's just going to be 2 theta times lambda. So lambda is some constant that we define. It's usually going to be between 0 and 1. I think we usually set it to like 0.9. And it's basically a scaling factor of how much we want to penalize this weight. So why are we even adding this term? This theta squared is simply making the weights positive, and we simply want to penalize having very large weights. So when we do our update rule, which is theta minus alpha times the derivative of this loss function with respect to theta, if this theta is really large, then it's going to have a really high loss, which will cause us to adjust the gradients accordingly. So that is why we add normalization. It just, once again, it penalizes very large weights. If you set lambda to 0, that just cancels out this term, so it might cause you to underfit a little more. If you set it to 1, actually I said that vice versa. If you set it to 0, cancels out this term, so you're no longer penalizing large weights, so that causes you to overfit. Whereas if it's set to 1, you might start to underfit a little bit because you might be penalizing your weights a little too much. There's other ways of tackling overfit, but that's just one that we're going to do for now. So weight initialization, a lot of times when you're initializing parameters, it might be tempting to just set everything to 0. So you can get decent results with that, but let's say you're working on some enterprise software and getting that additional 0.5% accuracy might be the difference between airplanes falling out of the sky or not. If you're flying, thousands of airplanes a day or something like that. You want to get as much bit of percentages as you can on your loss. So, oh yeah, I mean, yeah, in the event of automated driving, it's very relevant, if that ever, which I think it's getting close. Anyways, a better way of initializing weights is to make them approximately 0. So just adding some variance in the weights. The reason why we don't initialize weights to 0 is our partial derivatives will be very similar to each other. We call this having symmetrical weights or symmetrical derivatives. So in practice, that just tends to be really, just have poor performance. So you'll get better performance by initializing it to approximately 0, or trying to make your weights, initializing weights to some kind of distribution. So who here has taken statistics or knows what I mean when I say distribution? So I know if anyone's lost. No one here has taken the statistics class. Okay. Is everyone shy? Alright, respectful. So distribution, normal distribution, Gaussian curve. I don't know if I should show an image of this. You can just think of it as like probability of like what stuff should be. So machine learning does a lot of probability stuff. I can't really explain this right now. But basically we're just kind of mapping our weights into, I'm just going to say the term, I apologize for those who haven't taken statistics class, but I'm going to map our terms into just normal distribution, so that way it just simply scales up into that later on. So that's why we do Xavier initialization. It's just adopting some distribution. You'll figure out what that means, I guess, once you guys learn that kind of term. Last thing we're going to cover is batch normalization. So batch normalization is basically you're normalizing your neurons in each layer. So why might you do that? The verbatim term is it simply reduces your internal covariance shifts. So I'm going to give you an analogy. if you have a network that only learned how that it's supposed to train on whether it gets images and wants to tell the difference between cats and if you're not a cat. So if you get a hot dog, it's not a cat. If you get a cat, it's supposed to be a cat. But it's only ever seen black cats. So if you show it like a white cat, for example, it's never seen this before. So it just gives it the class it's not a cat because it has a high internal covariance. So by performing batch normalization on our neurons per each layer, it simply reduces that and allows you to generalize to other problems. I'm just not expecting you to be convinced of that right now, but just keep that in the back of your head. You're exposed to it. So yeah. Now we're going to get on to the less dry part of this lecture, which is going to be actual convolutional networks. So, here we go, Cody.
All right, so now I'm going to talk about convolutional neural networks, or CNNs for short. So what is a CNN, and how is it different than a normal neural network? Basically, it's a type of neural network that uses locality of the input data to find patterns, and this means that it keeps track of where the input data specific features are located. And in order to do this, it uses a sliding window, we can say, to look at the data section by section, and I'll go into this more in detail. And CNNs are normally used with images as inputs, so that's what I'm going to talk about today. So in order to be given as an input to the network, the image is represented as a three-dimensional matrix. The height and width of this matrix corresponds to the height and width of the image in pixels, and the depth, which is 3, corresponds to the red, green, and blue values of each pixel in the image. In a normal neural network, this three-dimensional matrix would be flattened into just one vector, and that would lose all the spatial correlation between the pixels. So just a little bit of history. CNNs began to be widely used for image classification after a CNN called AlexNet outcompeted state-of-the-art image classification models in a competition in 2012. And that basically proved how effective they were at image recognition and pattern recognition. All right, so how does the CNN work to find the locality in the image? It uses something called a filter. So this is the sliding window that I mentioned a couple slides ago. All it is a matrix of weights, and it's used to enhance visual patterns in the image and provides a measure for how closely a specific patch of the image resembles a visual feature. And to do this, it takes the dot product over each section, and I'll discuss that more if you haven't taken linear algebra. And in addition, the filter has an aspect of depth because, like I said, the input is going to be a three-dimensional matrix, not just a 2D one like you see here. To get into usage of how you would actually use a filter, first you superimpose it over a section of the image, and by the way, kernel is just another name for a filter. And then you do the dot product operation, which is just element-wise multiplication between the weights in the kernel and the corresponding weights in the section of the image that you're looking at. And then you add them all up, and you record the sum, and that's the dot product. And this is applied through the depth of the inputs. And so after you do one dot product operation, you shift the filter over a little, and you keep doing it again until you've gone through the whole input image. So here's a diagram of what an input and a filter could look like. As you can see, that's the input image. This is the filter. The filter is a lot smaller than the image, so it can detect different features in different parts of the image. And remember, the dot product returns one number. That's pretty important. So this is a breakdown of how the dot product operation works. So the matrix on the left side is going to be the section of the image that the filter is looking at, and then that's the filter or the kernel. So you multiply each element of the section of the image by the corresponding element of the kernel, like the top left and top left, and then you add them all up, all the products, and you get one number. And if the section of the image contains the same values but in a different order, then the output's going to be different. Okay, so stride, another important term, is how far the filter moves in each step as it slides across the input image. And it's measured in pixels, and you specify it as a hyperparameter when you're training the network. So the process of the filter sliding over the image is called convolution, and the output is the convolved feature. So this is like a little animation. You can see how the filter moves across the input matrix, and each dot product operation, the result is going to be a term in the convolved feature. So in this specific example, the input is a 5x5 matrix, and the filter is a 3x3 matrix, and the step size is 1 because it's moving one space over for each new operation. And again, in this example, it's only two-dimensional, but in real life, the image would be three-dimensional and the filter would be three-dimensional. So instead of being a 3x3 matrix, it'd be 3x3x3. So just some additional terminology. The the output matrix, or the convolved feature, is also commonly known as the activation map. And a stack of activation maps is called the convolutional layer. So here's a convolutional layer consisting of a stack of 6 activation maps. And each activation map is created with a different filter, so each one is unique and different. So it's very simple to calculate the size of the activation map with this equation. And it's important to know how big the activation map is going to be, because the activation map that you get from as a result of this is going to be the input into the next layer of the neural network.
So if you have multiple layers, you might notice that like your activation maps will just shrink. If you guys remember the 5x5 example with 3x3, so that just becomes an issue.
Yeah, I'll go over shrinkage a little more. So just a little practice. You see we have a 32x32x3 image, and then 5x5x3 filter. So if you plug these values into the equation, you get 32 minus 5 is 27, divided by 1 is 27, plus 1 is 28. So the result's going to be 28 by 28 by 1. And that was with a stride length of 1, by the way. So if we change the stride length to 2, then we have 27 divided by 2 plus 1 is 14.5. Because this is not an integer, it's going to cause a problem. So basically, as the filter moves across each horizontal row, when it reaches the end, it's going to hang off a little bit and not fit evenly onto the input. So because of that, this stride size isn't going to work for this specific input. Alright, so shrinkage. So as you can see, the activation maps are always smaller than the input, so 28 by 28 from the 32 by 32 by 3 image. And so the amount of data that you have is shrinking, and that means that there's going to be less information encoded in the data, so you're losing a little bit of information. And this can be a problem when you have a lot of layers and a lot of activation maps like stacked on top of each other. So to resolve this, we can use something called padding. So padding increases the size of the activation map by surrounding the input matrix with dummy pixels, which could be all zeros or all ones. And it's like a frame around the image that allows the filter to go further over the image than it could before without the padding. So here you can see the blue is the original image with a 5x5 input and a 3x3 filter. The activation map is going to be 3x3. But if you increase the size to 7x7 with the padding, then the activation map is going to be 5x5. Alright, so alternatively, you might want to actually shrink the image if it's too big, because if it's too big, then it might just require too many computations, too many parameters. It'll make the network train very slowly. So one way to shrink the image is to increase the stride size, and this basically results in fewer dot product operations and then a smaller activation map. But this isn't very efficient to shrink the image if that's all you're trying to do. A more efficient way is a pooling layer. So a pooling layer, it doesn't use a sliding filter like convolutional layer. It reduces the resolution of the image as a whole in one operation. And this can help solve a limitation of the convolutional layers, which is that they record the precise location of the feature in the input. And you want this to a certain degree, but if it's recording the location to like too great of a resolution, then that means that small movements of the input will result in a different activation map. So if you have like the same object, but it's like slightly moved, it will think it's a whole different object. And this will contribute to overfitting because it'll make it hard for the network to generalize among different inputs. So a common approach to solving this is to lower the resolution of the input so that it still contains the large and important structural elements, but it doesn't contain the fine detail that's not really necessary. So again, this can be done by using a bigger stride, but a pooling layer can do this with less computations. So the first type of pooling is max pooling. Basically, all it does is takes the max value from a specific region of the input and maps it to the corresponding region in the output. So you still have like a diagonal line here. And the other type of pooling is average pooling. And so this takes the average value in a specific region and maps it to the corresponding region in the output. So just to reiterate, using a convolutional layer with a bigger stride will have a more detailed effect than pooling, but pooling is much faster because it uses fewer operations. Alright, so this is an example of a CNN as a whole. So you can see it has many convolutional layers, and also uses a ReLU activation function, which is commonly used in CNNs. And so the layers are repeatedly applied on each other to transform it and detect shapes. And like Curtis mentioned before, the first layers on the left are used to detect like basic shapes, like maybe the ovals for the wheels and like the straight line for the windshield there. And then as you move to the right through the network, it can detect like a little more complex shapes, like maybe You can say like this is some sort of vehicle, and then towards the right of the network, you can say like this is a car. And if you had an even more complex network, you can go a step further and say like this is a Tesla Model S. So this is kind of a visualization of what the low-level features look like and the mid-level features. So the low-level features are just like lines and circles, and they get more complex as you move through the neural network. All right, so finally I'm going to talk about dropout. And before I do that, I'm just going to reiterate a little more about overfitting. So overfitting is when the neural network corresponds too closely with the training data set and can't be generalized to like additional data. And this happens when it's like too complex relative to the data. Underfitting is the opposite, where it basically doesn't learn a pattern in the data at all, and it's not complicated enough. So to reduce overfitting, you can use a technique called dropout. And dropout is basically where you turn off a set of neurons in each layer of the network. And the set that you turn off is random. You control it by giving each neuron a probability that it'll be on or off. So it's often set to 0.5, so that means that in each pass it's going to be random 50% of the neurons that will be turned off. And so by doing this, you introduce a certain level of noise and variance into the network, and this basically forces it to generalize because in each layer the data isn't exactly the same.
You also don't have like one neuron just holding everything hostage because it's really large, because it gets turned off half the time.
All right, and if you use dropout, after you train, the weights are going to be abnormally high because simply you didn't train it with the entire data set all at once. You just used like part of it. And so to fix this, we just can normalize the weights by lowering them proportional to the ratio of neurons that were turned off. So you can do this by scaling each weight by 1 over p, p being the probability. All right, so this is a visualization of what the filters can see. Yeah, so you can see like what part of the input the filter is going over, and all of those are just like different filters that you can apply. And when you use different filters, it kind of highlights different aspects of the input image. Like in this one, you can see it highlights kind of the bottom horizontal edges, and this one kind of highlights the top horizontal edges. All right, and finally, I'll show you what a simple implementation of this looks like using PyTorch, which is a pretty powerful machine learning library.
We'll send out another email for the slides that you fill in the workshop if you guys want to see it.
Okay, so what this is basically doing is classifying images in the CFAR10 dataset. So the CFAR10 dataset is a dataset of 60,000 32 by 32 color images that are separated out into 10 classes with 6,000 images per class. So these are the classes here. It's just like pretty simple objects. And it's also split into 50,000 training images and 10,000 test images. So this is just showing an example of 4 random images: a bird, a plane, a car, and a frog. Alright, so this is where we define the convolutional neural network. We specify the layers and the forward propagation.
So So in this model, and in that module is a PyTorch class. So we're just inheriting from that. This specific model that he made has 2 convolutional layers, has a pooling layer, and then 3 fully dense layers at the very end, just so we can get like actual classification out. And we're using rel here as our activation function. Oh, we're actually using 2 pooling layers in the fall.
Yeah. So then you just need to define a loss function and an optimizer. So here we're using cross entropy loss. And for the optimizer, it's a stochastic gradient descent with momentum.
I didn't know you didn't do atoms. That's all.
All right, so this is where you actually train the network. I did 4 epochs. So this is the part where you can like play around with it and get like better results. So this is a pretty short training. It only took like 5 minutes. But you can see that for each epoch, the loss is decreasing. You can see a visualization of that there. And then you just save it to, you save your model to a file. So testing the network on the test data. These are 4 images that it's going to be tested on. This is what they actually are: a cat, a ship, and a plane. And as you can see, it predicted that it's a cat, a car, a plane, and plane. So it got 2 out of 4. Not too bad.
That's interesting classes. I think the right one is a bird.
And then this is how it performed on the whole data set. The accuracy on the 10,000 test images was 58%. But an important note is that if this were choosing randomly, it would have an accuracy of about 10% because it's randomly picking a class out of 10 classes.
It's also not using patterns.
And then this is the breakdown of the performance by class. Yeah, that's it.
Alright, thanks guys. I don't know if there's any pizza left. There's one more slice. Let's fight for that. We're going to linger around a bit if you have any other questions. Thanks for joining us.
And if you haven't already, could you please sign in?
It's recording on my laptop. Yeah, so do you remember weather networks? There's just yeah, so a filter might just be like 3 by 3 by 3 by times the plus now. Choose the weights. So Xavier initialization is always you make it 0, approximately 0. Remember the weight initialization slides? You just want to initialize it to like something that has some weight. Oh, yeah, so optimization. So remember the gradient descent rate? Beta minus alpha. Basically, that is what you use to actually move the weights. So that becomes more accurate. Yeah, we get a better filter.
Just one because I can see that for the
No, you have multiple. So like in his network, I don't remember, it might be like
I'm not going to be able to stay for the e-board meeting.
That was a small one.
So I'll look at the notes here.
center points. You know, sometimes you may meet the center point, and maybe that will be just the create
I don't know what the single point is, but like the number of filters you have is different forever, so you can just specify. It's kind of like, choosing number neurons. You don't know.